So, hello everyone. I'm Gitanjali. I'm a PMRF scholar from IIT Delhi. So, welcome to the live section of this course, Physics of Linear and Nonlinear Optical Waveguide. So, as I discussed in our previous live session, we'll discuss the problems that is related to the week 4 content, and as well as I will try to solve the doubts that you must be having for the assignment or any conceptual doubt. So we'll cover all of this. So please wait for 1 minute. Let me connect my tab. So I think the screen is visible now. So let me go through questions. Okay. So the first question, it's okay. Uh, so in this week we have gone through the planar symmetric waveguide, and we have tried to solve what are the different type of modes that is supported by this planar waveguide, as well as what are the wave equation, what are the propagation constant, and how it depends on the p parameter. So based on this concept, we'll go through few numerical problems. In between, while solving the problems, if you have any doubt during the step, so please feel free to stop me at that moment so that you can clarify your doubt at that point. Okay. So let me start. So the first question, it's based on the planar waveguide. So it says consider a planar waveguide having co-refractive index 1.5, cladding refractive index 1.48, and co-radius it is 1.5. So find the wavelength range at which the waveguide is single moded. So for single mode operation, we need a condition on the V parameter. So if you recall the graph between eta and zeta that we have seen in the class. So we have a plot like this. So this shows the variation of eta with theta. And we have uh, two types of solutions. So we got the solution through the intersection. So there are odd modes. This is even mode, and there are odd modes. So they occur alternatively, and we have a equation of a circle like this, and the intersection between this circle with the transcendental equation. So this will give the allowed solution for our waveguide. So these are the allowed solution for different values of V parameter. And if you recall, these are the points pi by 2, pi, 3 pi by 2. And at this point, the solution is diverging, right? And for single mode operation, we need V parameter should be less than pi by 2. And V parameter, the definition is same for all types of structure. If the structure is waveguide or fiber, the definition is the same. So it is K0A root over of n1 square minus n2 square, which should be less than pi by 2. And K0, we know it is nothing but 2 pi over lambda 0. And this is co-radius n1 square minus n2 square, which should be less than pi by 2. So we want the wavelength range. So for this, lambda 0 must be greater than 4a root over n1 square minus n2 square. And all these parameters are given. The co-radius is given, it is 1.5 micrometer. N1, it is given 1.5, and N2, it is given 1.4. So if you put these values, you will get a value around 1.465 micrometer. So that means if the operating wavelength, so if the source you are using, if the wavelength of the source is greater than 1.465 micrometer, then the waveguide, it will behave like it will support only single mode. And when the wavelength it is less than 1.465 micrometer, so the mode supported by the structure, it will increase. So it will be multimoded operation. Okay, so the answer will be lambda 0, it must be greater than 1.465 micrometers. So let us move to our next problem. So it says consider a steep index planar waveguide with the following refractive index profile, which is n, it's a function of z. Then it was asking what are the non-vanishing components of TE and TA modes for a mode propagating along the x direction. So now we have variation of refractive index along the z direction, and is asking about what are the non-vanishing terms, components for TE and TA mode. So if you recall, for a planar waveguide, so we have two types of solution that will exist. One is TE mode and another one is TA mode. And for TE mode, we have will be no electric field along the propagation direction. So no electric field along x direction. And for TA mode, there will be no electric field along, sorry, TM, it will be no magnetic field along its direction. And the components, we have got the components by using the field expression. So this is the general field equation for the planar waveguide, which is the propagation along x. So using this, and if we put this expression into the Maxwell's equation, then we can get what are the non-vanishing components of TE and TMO. But that will be a lengthy process. But other way to find out how you can determine what will be the non-vanishing components of TE and TM mode for a different types of profile is that So just look at what are the plane which have the refractive index variation as well as the propagation direction. So the propagation is along x direction and there is a variation of refractive index along the z direction. So this is xz plane, which has the variation of refractive index as well as the propagation of the mode, right? So that means you can say the T mode. It will have EI component which is perpendicular to this plane as well as other components will be the magnetic field. Okay. And for TM mode, it will have no magnetic field in the so the component will be HY and other component in the plane extent plane will be the electric field EX and EZ. Okay, so this is how you can calculate, you can determine what are the non-vanishing components of TE and TM mode for a given profile. In the class, in the lecture, it was like the variation is along, if I recall, so the variation is along NX, refractive index variation, and there is propagation of, wave along the Z direction. So the plane is same, XZ. So T mode, it will be EY, HX, SZ, and TM mode, HY, EX, EZ. Okay. So I hope this problem is clear. So this is a conceptual one. So let us move to our next problem. Please go through the question once. So we have the dielectric step index symmetric planar waveguide, not written clear. Okay, so if it is not visible, let me read out. So there is a dielectric step index symmetric planar waveguide, which is refractive index N1. I think this color is visible. So, so N1 it is 1.5, N2 it is 1.46, and it's a symmetric step index planar waveguide. And the A parameter it is 2 micrometer. Just the value of lambda 0 is so lambda 0 value is 1 micrometer. I think this goes. Lambda 0 is 1 micrometer. Okay. So now the question is asking what are the number of symmetric as well as antisymmetric modes at lambda 0, 1 micrometer. And the second part is find out the waveguide thickness for the waveguide to be single moded at lambda 1 micrometer. Okay. So maybe so we have already have lambda 0 equal to 1 micrometer, but let us see what are the number of modes, symmetric and antisymmetric modes. So for that, we need to find out what is the V parameter first. So V parameter, it is given by is 2 pi lambda 0 a root over of n1 square minus n2 square. All the parameter is given. 2 pi, a is given, it is 2 micrometer, and n1 is 1.5 square, n2 is 1.46 square. And if you calculate it, it will come around 1.45. Okay. And to find out what are the total number of modes, there is a trick. So you can get the solution by looking at the profile and finding which circle this V correspond to. So this circle have different values of V. So according to the circle, you will get what are the symmetric mode and what are the antisymmetric mode. But there is a trick also to find out the total number of modes in a step index fiber. What you have to do? So total number of modes. So we have to divide the V parameter by pi by 2. Okay. And whatever you get from this equation, what you need to do, we have to look for a integer that is greater than this value, but it is closer to this value, but it is greater than. Okay. So then you have to find out the nearest greatest integer. So let us see, we have V is 1.4 pi and we have to divide it by pi by 2. So this will come around 2.8. So this will be 2.8 only. And the nearest greater integer, which is closest to 2.8, is 3. So that means this waveguide supports total modes, which is 3. Okay. So now to find out among these 3, what are the number of symmetric and antisymmetric modes? You can see here in the graph. So in the graph, you can see this odd and even mode, they repeat alternatively. So that means what you have to do, you have to divide it into equal parts. Let's say it's an even number, the integer you got. So if it is an even number, then you will get even number of means equal number of symmetric and equal number of asymmetric mode. And if it is a odd number, then it will be like both the symmetric and antisymmetric mode will have equal parts, but the uh, highest so the additional part that is making it a odd mode. So this will go to the even mode. So what I mean, it is a 3. Here it is a 3 means odd number. So divide it into equal parts. So 1 1. So now it is 2. So other one, it will goes to the even. Okay. So this means we have 2 symmetric modes and 1 antisymmetric mode. So let us say we have 4, we got 4. Then there will be 2 number of symmetric mode and 2 antisymmetric mode. If it is 5, then there will be 3 symmetric mode and there will be 2 antisymmetric mode. Okay. So, and there is a formula also. So, in general, if V lies between m pi to m plus half pi, where m is 0, 1, 2, Then in this case, we'll have m plus 1 symmetric mode and m number of antisymmetric mode. But instead, if V lies between m plus half pi to m plus 1 pi, then in that case we have equal number of symmetric and antisymmetric mode. So you can use the formula or you can before. So just if it is a odd, just find out what is the nearest even number, then divide it by 2. Then that will goes to the symmetric and antisymmetric mode. And the additional, the one mode, it will goes to the even mode. Okay. So do it as you, so as you think it is the easiest part. Okay. You can use the formula or you can do like this. So here if you see, we have V is 1.45, right? So this you can write. So this is less than 1.5 pi, right? Which is 1 plus half pi. So that means m here is 1. So if you use the formula here, it will be like it has 2 symmetric mode and 2 antisymmetric. So I hope this is clear. So let us move to our next part. So the fourth question, it's the easiest one. So the question is like the number of guided symmetric and antisymmetric modes for V lying between 11 by 2 pi to 6 pi. So if the question says like this, then here you don't know the what is the value for V. So here you can see this is 6 pi, which you can write it as a m plus 1 pi, right? You can't write 6 pi as m plus half pi. So that is why you can write it as a m plus 1 pi. So that means m here is 5. So we'll, if you see the formula, so for this situation, we have equal number of even symmetric mode, and the number is m plus 1, which is 6. And the antisymmetric mode, it is all 6. So that means the answer will be B, 6, 6. Okay. So let us move to our next problem. So we for this question, so it says consider a symmetric planar dielectric waveguide which has refractive index profile nx, which is n1 for mod x less than a, and it is n2 for mod x greater than. Assuming the propagation along y-axis, write down the non-zero field components of TE modes and obtain the condition on A for the waveguide to support only one TE mode at lambda equal to one. I think I have skipped the second part. Sorry. Oh, this part I have missed. Now only I recall. So we miss this part. Okay. So let me calculate it first. This question is similar to what is the question we're going through now. So it was like the waveguide thickness for waveguide to be single moded at lambda 0 equal to 1 micrometer. In the first part, we see what is the total number of modes, which is 3. So it's not a single moded operation at lambda 0 equal to 1 micrometer. So for single moded operation, what we need, V should be less than pi by 2. So that means, so just put the definition of V, K0a root over of n1 square minus n2 square. It should be less than pi by 2. So that means 2a, which is the film thickness, waveguide thickness, it should be less than lambda 0 by 2 root over of n1 square minus n2 square. And all these are given. It is 1 micrometer, it is 1.5, it is 1.46, and if you calculate it, it will come around 1.45 micrometer. Um, okay. So for the second part of this fifth question, we want to find out obtain the condition on A for the waveguide to support only one TE mode at lambda 1.5 micrometer, N1 is 1.45 and N2 is 1.44. So this is somewhat similar to question number 3. So let us quickly solve it. So to find out what are the non-vanishing component for this waveguide. So as I said before, we have to first look for the plane, which has variation of refractive index and the propagation direction. So this is nx, and the wave is propagating along y-axis. So xy plane. So that means the T mode, which has zero electric field component along the propagation direction, it will be in the z direction, Ez, and the other component are magnetic field, Hx and Hy. So these are the non-vanishing components of TE mode. And for single mode operation, as we see, so as we saw in the last question, V should be less than pi by 2. So A should be less than lambda 0 by 4. Now in the question, it was asking about the core radius. Sorry, the first part, it was not asking about the thickness. It is asking about what is the value of A. So that means it is lambda 0 by 4 root over of n1 square minus n2 square, and is given 1.5 micrometer. This is given 1.44, and it is 1.45, and this is 1.45. And this will come around 2.2058 micrometer. So for the waveguide to be single moded, A should be less than 2.205. Okay. So let us move to our sixth question. So the sixth question, let me read out. It says the fundamental mode of a symmetric tape index planar waveguide at its core cladding interface is 50% of its maximum value. Then find the V parameter of this waveguide and write all the guided modes supported by it. Okay. So we have a symmetric. So let me draw the refractive index profile. So it is symmetric. So we have, let's say this is NX and this is, so here it is x equal to A and it is x equal to minus A. And this is, let us say it is N1 and the cladding is N2. Okay. And it is given at the core cladding interface, that is at x equal to A or x equal to minus A. The field value, it is 50% of its maximum value. So if you recall the fundamental mode of this symmetric planar waveguide, what is this? It's the even mode. So now we are completely focusing on TE mode. So we haven't discussed TM mode. When it will be discussed in the class, we'll go through this some of the problem that is related to TM mode. But for now, all the problems, these are based on TE mode. Okay. So if you recall even mode expression, the fundamental mode is A cos kappa x, right? So this is the fundamental mode. And in the question, it is given, let us say this is psi of x, or if you go through the electric field expression, it will be Eyx. So it is given Eyx at the core cladding interface. Let us say we are looking at x equal to A. It is half of its maximum value. So what is the maximum value of Eyx? It will be A, right? When kx equal to 0, it will be A. This is half of A. And the left hand side, the expression is A cos Ka, which is equal to A by 2. So that means cos Ka, it will be half. And so our final, find out what is the value of V, right? And if you recall, there is a expression, there is a relation between zeta, eta, and V. So zeta square plus eta square, it is V square, right? So if you can find out this zeta and eta, then we can easily find out what is the V parameter for this symmetric waveguide. So for zeta, if you recall, zeta is nothing but A, right? So, and in this relation, we can easily find out what is the kappa A value, because cos A, it is half. That means kappa A, it will be pi by 3, right? For the fundamental mode. So this is equal to zeta. And what is the expression for eta? So eta is, if you recall, it is zeta tan zeta, right? So we know the value of zeta. Now we need to find out what is the value of tan zeta. So for this case, we know for the values of cos k, So let us, or you can directly put the value of zeta pi by 3 here. So this is pi, then pi. So kappa is pi by 3 and then pi by 3. And this will come around pi by 3. This is root 3. So pi by root 3. Okay. So we got the value of eta now. Now we can easily find out what is the value of v parameter. So b square is theta square plus eta square. Zeta square is pi by 3 square and eta square is pi by root 3 square. So this will give 2 pi, sorry, this will give 4 pi square over 9. So that means v is 2 pi by 3. So we got the value of v now. And to find out the modes, number of modes, as I said before, we have to divide the v by pi by 2. So this is 2 pi by 3, pi by 2. So this is 4 by 3, which is 1.33, and this is less than 2. So that means we have, this is a even number, so we can divide it by 2. So this is equal number of symmetric and antisymmetric mode. So the lowest one will be the fundamental mode. This is the antisymmetric mode. Okay. So we got is 2 pi over 3, and the supported modes are T0 and T1. So let us move to our next problem. Please go through the question once. So it is based on a mirror waveguide. So if you coat the cladding, the surface of this two core cladding interface by some metal, then what will be the wave equation? What will be the propagation constant? How the wave behaves inside this mirror waveguide? Okay. So let me read out the question. So consider a dielectric slab of thickness 2a and refractive index N1 is sandwiched between two perfectly conducting surface so that the propagation constant beta of a TE mode can be expressed as beta is this value. And these are the condition given when it is 135, M is 135. So these correspond to symmetric mode, and when it is 246, this correspond to antisymmetric mode. So we need to find out the value of beta. So let us see what is the wave equation inside the guiding region. So wave equation inside the guiding region from 0, x, and 2. Uh, what is the wave equation? This is d square ey over dx square plus k0 square n1 square minus beta square ey should be 0. And this we have termed as kappa. So d square ey over dx square plus kappa square ey is 0. And for the wave guidance, what we have, beta should be less than k0 n1, right? Should be less than k0 n1, so that the wave will be oscillatory. It will be a propagating mode solution inside the core region, and outside it will be a decaying wave solution. But here the cladding layer itself is a metal, so it is totally reflecting. That means the field outside this core region, it is itself zero. Okay, so this implies k square is greater than 0. So when k square is greater than 0, so we have the solution Eyx. So this thing I think you know, it is combination of sine and cosine. So to find out what is the value of A and B and kappa, we need boundary condition. So what is the boundary condition here? One is it's a perfectly reflecting metal surface. So that means at the interface, that is at Ey at x equal to 0. So here and here, the field should be 0 beyond this value. Okay. So Eyx, it should be 0, and Ey equal to 2a, it should be 0. So if you put the first one into this equation, so this will have b equal to 0. That means Eyx, it should be a sine kappa x. And from the second relation, we have Ey x equal to 2a, it should be 0. That means a sine 2 kappa a, it should be 0. So 2 kappa a will be m pi. So kappa will be m pi by 2. Right? So Eyx now we have a sine m pi x 2a, or m is 1, 2, 3. So what will be the propagation constant then? So if you recall, kappa is nothing but k0 square n1 square minus beta square, which is m pi over 2a square. And if you square it both sides, so we have k0 square n1 square minus beta square. So there won't be any square here. Here it will be m pi by 2a square. So beta we already got. Beta square, it will be k0 square n1 square minus m pi over 2a. So that means we have calculated this part, beta, and m, sorry, uh, for the even and odd mode, which value of m correspond to even and which value of M correspond to odd mode, you can look at the field profile. So we have this mirrored surface. This x equal to 0, x equal to 2a. And we have Eyx, a sine pi x by 2, m pi x by 2a. When m is 1, it will be Eyx is a sine pi x by 2a. That means at x equal to a, if you put what is the value of this field at the middle, so this will be a, right? So that means the field is maximum at the center and it is 0 at the boundary. It is nothing but a even mode, right? And if you look at the higher order mode, so this will be like this, which is the odd function. Okay. So this will give 1, 3, 5 odd number will correspond to symmetric mode, and m equal to 2, 4, 6, it will correspond to antisymmetric mode. Okay. So we'll move to our next problem. So the next problem is related to same planar mirror waveguide. So in this session, I will try to cover the things that is not covered in the lecture. So I will give some additional problems, or like in the class, if you recall, only symmetric one is discussed. But in this session, I will also discuss what will be the field profile when you have antisymmetric waveguide. Okay. So we'll cover the problems that hasn't been discussed in the class. Okay. In planar mirror one, it's not discussed in the class. So if while solving, if have any doubts, so please stop me at that moment. Okay. So let us see what the question 8 says. So consider a planar mirror waveguide with refractive index and 1.46 2A, it is 2 micrometer at wavelength lambda 0, 0.6 micrometer. Now the question is asking what is the effective index of the second mode. Okay. So second mode, that means m equal to 2, and effective index, it is nothing but n effective is beta over k0. So it will be beta, we have already calculated it. So it was beta is square root k0 square and 1 square minus m pi by 2a whole square. So beta by k0 will be square root and 1 square minus m pi 2a k0 square. So all the parameters is given, n1 is given 1.46, and for the second mode it is m is 2, right? Lambda 0, it is given, so you can calculate k0 from it, which is 2 pi over lambda 0, and a is also given, it is 2 is 1 micrometer, so A will be, let us say 2 is 1 micrometer. And if we put these values, so N effective will come around, this will 1.46 square minus 0.6 square half, which is 1.33. So the answer will be option C. So let us move to our next problem. It's a conceptual one. The next one. The question says, which of the following is not true for a symmetric planar waveguide? The first option is fundamental mode is an odd mode. So if we recall, the fundamental mode, that is T0 mode, it is A cos kappa. So fundamental mode, it will be always a even mode. So that means this is not correct. This is not true. So answer can be A. And second is, as the mode number increases, the propagation constant decreases. So if you recall, so what is the relation between mode number and propagation constant? So this we can get it by looking at the graph between theta and zeta. So this graph gives what are the allowed solution, how the zeta value varies, how the v values varies. So we have even, odd, even, odd. And when v parameter increases, the number of modes that is supported by the structure, it will increase. Now, if you look at this point, the point here and the point here, this is T0, this one is for T1. So this is the value for zeta and eta. So that means zeta for TE1, it is greater than zeta for T0. So zeta is nothing but, so if you square it, zeta square for TE1 should be greater than zeta square for TE0. Zeta square is kappa I square, which is T0 square N1 square minus beta T1 square, and T0 it is K0 square N1 square minus beta square T0. So this cancel. So we have beta square T0 is greater than beta square T1. So for the same waveguide, if it supports more modes, then as the mode number increases, the beta value it will decrease. Okay. So fundamental mode it will have highest value of beta. So that means this option is correct. So this can't be answered. So for the next part, for the waveguide to be single moded, B should be smaller than pi by 2, which we have seen it should be less than pi by 2. Next thing is option D is the propagation modes penetrate more into the cladding as the mode number decreases. Okay. So the propagation mode, that is the mode number. So penetration into the cladding. So it depends on the value of alpha. So if we recall the field in the cladding, you can write it as C e to power minus alpha x. So C over e to power alpha. So that means when alpha is high, that means the E field, it is lower, right? That means when alpha is high, the penetration into the cladding, that is the energy leaking into the cladding, it will decrease. So for this, so now let us see how alpha depends on beta. Because mode number is related to beta. So if we can somehow relate beta with alpha, then we can find out the answer. So alpha is nothing but beta square minus k0 square into square. So it directly depends on beta. So that means if mode number is decreasing, so beta value, it will increase. We have seen in the previous part. So when beta value will increase, the alpha value will increase. Give lower penetration into the cladding. So that means lowest mode, the clicking to the cladding by the lowest mode, it is smaller than the higher order mode. So this option is also not correct. The penetration of modes, sorry, the propagation modes penetrate more into the cladding as the mode number decreases. So this is also not correct. So answer will be option A and D. Okay. So let us move to our next problem. So question says, consider a symmetric planar dielectric waveguide if the intensity of its TE0 mode, which is a fundamental mode, at the core cladding interface is 50% of its axial value. Then obtain the number of modes supported by the waveguide. So to calculate number of modes, what we need? V parameter. So given the condition, we need to find out what is the V parameter for this waveguide. So recall for symmetric waveguide, we have A cos kappa x for x less than mod A. This is for symmetric mode. If it is antisymmetric, then that will be sine. So I am writing it for the TE0 mode. Okay. And in the cladding, we have C e to power minus alpha x mod x for x greater than mod A. So this is for symmetric. So TE0 mode, it's a fundamental mode. So that means it will have A cos kappa x. And what is the value of this T0 mode at the axial position? T0 at the axial value. That means at the axis of the waveguide. So axis means at the center of the waveguide. Okay. Let us say the center is at x equal to 0. So this will be A. And at the core cladding interface, it will be A cos kappa. And it is given this value, it is half of this value. So that means A cos pi, not sorry, it is given the intensity. The intensity of T0 mode at the core cladding interface is half of its axial value. So if you recall, intensity is directly proportional to EY square. So instead of comparing the field value, we have to compare the intensity now. So that means we need to square both the sides. So A cos kappa is square. It is half of the intensity at the axial value, which is A square. So what we have now, cos square Ka, it is half, that means Ka. So cos K is 1 by root 2. So this will give Ka as pi by 4. So we have the value of zeta now. So for eta, we need zeta tan zeta, which is K tan Ka. K is pi by 4 tan pi by 4. So this is pi by 4. So zeta is equal to eta. Now for V, we need the relation V square is zeta square plus eta square, which will give V as 2 root zeta, because zeta equal to eta. So 2 um, 2 root, no, this will give root 2 zeta, right? Because zeta square, if you take the square root, it will be zeta, and there is root 2 here. So root 2 pi by 4. Pi root 2 by 4. So we got the V. Now for planar waveguide, we need to divide it with pi by 2. So 2 will cancel, pi will cancel. This is root 2 by 2, which is 0.707. So this is less than 1, right? So the number of modes that the waveguide support is, it is 1. So that means the waveguide support only the fundamental mode, which is TE0. So always in the question, please see whether the field is given or the intensity. So instead of taking intensity, if you would have taken field, then you will get wrong answer. Okay. So let us see question 11. So it's based on a symmetric step index fiber, not fiber, waveguide. Okay. So consider an asymmetric step index planar waveguide with the following refractive index profile. So N1 is greater than N3, greater than N2. Find out the TE mode wave equation and the corresponding field expression in different regions of the waveguide. And what is the condition on beta for the guided mode inside the waveguide. So first, let us look at the profile. So we have next versus X. So this is N1, this is N3, this is N2. Let us say this is X equal to minus T, X equal to 0. So what are the non-zero component for T mode? This is if you assume the wave is propagating along Z direction, so it is Ey Hx as. So let us see the model analysis. So we have Nx, it is N2 for x greater than 0, and it is N1 when x lies between minus t to 0, and it is N3 when x is less than minus t. So the general wave equation will be, it is d square Ey dx square plus k0 square n square x minus beta square Ey is 0. So first we need to find out what is the range of beta. So for guided mode, if you recall, we need beta to lie between N1 to N3. So while here, the beta value it should lie here. So we have thoroughly discussed in one of the live section. If recall, if beta lies here, then it will be a propagating mode in this region, and here it will be a exponentially decaying solution. But if it is beta lies here, then it will be a propagating solution in both N1 and N3 and decaying in N2. That means the energy is leaking to the cladding region N3, which we don't want. So beta should lie between N1 to N3. Okay. So let us see. So let us see the reason now. For x greater than 0, we have d square Ey over dx square plus k0 square in x greater than 0 and x is n2 square minus beta square Ey is 0 and beta it is greater than n2, right? Because beta is greater than n3, that means beta is greater than n2. So here we can write it as d square Ey dx square minus beta square k0 square n2 square Ey is 0. So let us say this value is alpha 2 square. So we have d square Ey over dx square is alpha 2 square Ey. And the solution for this is Ey is e to power minus alpha 2x plus b e to power alpha 2x. But in the reason x greater than 0, this is the amplifying solution, which we don't want for the guided mode. So that means this term we can neglect for the guided mode. So Eyx will be a e to power minus alpha 2x. So alpha 2 is square root beta square minus k0 square n2 square. Now let us see the other reason, other cladding reason. Okay, so let us see co-reason first. D less than x less than 0. So here we have nx is n1 and beta here is less than n1. So that means the wave equation d square ey over dx square plus a0 square n1 square minus beta square ey, it should be 0. This is already positive. So d square ey over dx squared, it is minus kappa square ey. So for this case, we can write Eyx as b e to power I kappa x plus c e to power minus I kappa x. So this is the field inside the co-region. The kappa here is k0 square n1 square minus beta square. Now the last reason, which is x less than minus t. So this will be similar to what we have in the other cladding reason, but here the refractive index is different. So we have d square ey x square k0 square n3 square minus beta square ey is 0. So let us say alpha 3 square, it is beta square minus k0 square n3 square. So this will give Eyx d e to power alpha 3x plus f e to power minus alpha 3x. But in the negative side, this is amplifying, so we can neglect it for the guided mode. So we have Eyx now is d e to power alpha 3x. Okay. So to find out what are the values of A, B, and what is the transcendental equation, we need to use the boundary condition. So first we got it was minus alpha 2x. The co-reason we have B e to power alpha should be kappa plus C e to power minus kappa x or minus t 0. And in the third reason we have d e to power alpha 3x. So at the boundary, we just need to equate the field values. Okay. So at x0, field values and the derivative should be continuous. So Eyx, let me directly write. So Eyx in the left hand side is b e to power I kappa x plus c e to power minus I kappa x equal to a e to power minus alpha 2x, x equal to 0. So this will give b plus c equal to a. So we got equation 1. Another is to equate the derivative, that is dy by dx. So this will, if you put it and calculate it, you will get a equation alpha to a equal to I kappa b minus c. So just uh, use the field equation to get the derivative, and this relation will you will get. Okay, and the other value is set x equal to minus t. Same thing. We have to relate the field values as well as the derivative. So if you put it, you will get b e to power I kappa d plus c e to power I kappa d equal to d e to power minus alpha 3d equation 3, and the derivative, it will give b I kappa will be there, b e to power minus kappa d minus c for I kappa d, it will be alpha 3d e to power minus alpha 3d. So just simplify this four equation to eliminate the constant a, b, c. So we have four equation and four constant. So if you do it, you will get a transcendental equation tan kappa d equal to alpha 3 by kappa plus alpha 1 by kappa, alpha 1 or alpha 2, alpha 2. And whole divided by 1 minus alpha 3 alpha 1 by kappa square. So if alpha 3, alpha 2 and kappa is given, then you can find out what is kappa and what is the propagation constant. Right? This will be the final transcendental equation. Now let us move to our next problem. So the next problem, it may seem similar to what we have seen in the first two problems. Like we have solved this problem before also, but here the concept is totally different. So let us see how. So it is given, consider a symmetric planar dielectric waveguide. If the amplitude of the electric field of its TE1 mode at the core cladding boundary, it is half of its maximum value, then what is the value of V parameter now? So this we have seen earlier also, but here we need to be careful while calculating the value of kappa A. So it's given TE1 mode. So it is a mode next to fundamental mode. So this is a odd mode, and it has expression A sine kappa x. And what is the maximum value of this A sine kappa x? So it will be A, right? And it is given A sine kappa x at x equal to A is half of its field value at the maximum. So this will give sine kappa A is half. So you can easily guess chi A now will be pi by 6, right? This is what you can easily guess. Like it will be pi by 6, but it is not the answer. This is incorrect answer. Okay. So for this, so whenever you are trying to solve this kind of problem, always keep the graph between zeta and eta in mind. Okay. Because the T0, T1 mode, they have different values of zeta. So if you recall the plot here, so this is the odd mode we are talking about. So there is a even mode also here. So this is the fundamental mode TE0 and this is the TE1. So for the TE1 mode to exist, you can see this is the zeta value, this is the eta value, this is pi by 2, this is pi, this is 3 pi by 2. So you can see here the TE1 mode lies here. That means the zeta value, it should lie between pi by 2 to pi. So pi by 6, it doesn't lie between pi by 2 to pi, right? So that means pi by 6 only answer. It is not correct. So what is the other guess for sine k equal to half? It is 5 pi by 6, right? And this lies between pi by 2 to pi. So that means the correct answer should be 5 pi by 6 instead of pi by 6. So you need to be careful here. So zeta value, it is 5 pi by 6. So what is tan zeta now? It will be tan 5 pi by 6, which is 1 by root 3. So now you can easily calculate what is eta. Eta is zeta tan zeta, which is 5 pi by 6 and 1 by root 3. Now just use the relation zeta square plus eta square is v square. So v square will be 5 pi by 6 square and 5 pi by 6 root 3 square. So this will give 5 pi by 6 square 4 by 3. So that means v now is 2 by root 3 5 pi by 6. So we have 5 pi by 3 root 3 for the v value. So the question was asking about this only, like what is the value of v. So for mode, as I've said before, just divide the v value by pi by 2 and look for the integer that is greater than this v parameter, but it is closer to this v value. Okay. From that, you can find out what is the number of symmetric and antisymmetric mode. So is this problem clear to you? Otherwise, we'll move to our next problem. Okay, good. So let us see the next problem. Next problem is a conceptual one. So it says so that if n square minus of x is n square x, that is the refractive index it's a even function of x, then the model field patterns are either symmetric or antisymmetric function of x. So we have utilized this concept to find out what are the modes of a symmetric planar waveguide, right? So now we'll see how uh, we have this uh, kind of profile whenever we have n square x is n square minus x. So what is the TE mode equation? So always remember this equation because it's the point where you can start to find out what is the propagation constant, right? So we have this general solution for T mode equation. So that means you can rearrange it to d square by dx square plus a0 square and square x. Eyx is beta square Eyx. So this is a eigenmode equation. If you recall the eigenmode equation, you can see the eigenoperator is same here and there is a constant value beta which is nothing but the eigenvalue. So we have this eigen equation. Now in the same equation if you replace x by minus x. So the dx, the double derivative it won't change. So d square by dx square plus k0 square is the constant, it won't change. N square plus x will become minus x, but it is already given, it is n square x, right? And the operator is ey minus x, and here we have beta square ey minus x. So if you see, we have d square by dx square plus k0 square n square x ey minus x as beta square ey minus x. So if you now compare 1 and 2, you can see this eigen operator, this operator eyx and ey minus x, they have same eigenvalue equation and same eigenvalue which is beta square. So this is only possible when they are some scalar multiple of each other, right? Let's say it is lambda, the scalar is lambda. So that means if you now again operate x2 minus x, this will give ey x lambda ey minus x, and ey minus x you can put this value will be lambda times eyx, which is lambda square eyx. So ey will cancel. So that means lambda square it is 1. Lambda is plus or minus 1. So we got ey minus x is plus or minus eyx. So this is itself the symmetric and antisymmetric condition. So if it is plus eyx, it's a symmetric mode. And if it is a negative of eyx, it is antisymmetric. Okay, so that means whenever symmetric planar waveguide will be there, we can divide the propagating mode to even and odd mode. Okay, so let us move to our next problem. It is also a conceptual one. So if you know the concept, then you can easily find out the option that is correct for this given question. let us see. Question says consider two symmetric planar waveguide satisfying the following relation. That is, V2 is greater than V1. The V number allows propagation of only one mode in the first symmetric planar waveguide, while the second planar waveguide supports propagation of two modes. So we have two symmetric planar waveguide, which is value V1, V2, and it is given V2 is greater than V1, and it is also given. So the V parameters are such that the first symmetric, it supports only one mode. So that will be a fundamental mode, T0. Let us say it is propagation constant, β01. And for the second, it support two mode. That means it will be T0, TE1. So let us say it is value β02 and β1. Okay. So now the question is asking which one of the following is correct for the symmetric planar waveguide. So let us see what's the push. Option A says. So option A is propagation constant of the fundamental mode is same in both the waveguide, which is not correct because when V2 is greater than V1, then β2 is always greater than β1. Okay. So as the V number it will be higher, then the fundamental mode, they are more confined in the core. So that means β2 will be greater than β1. So this is not correct. Next option is the second waveguide have a larger acceptance cone as compared to the first waveguide. And if you recall the acceptance cone, it depends on the numerical aperture, right? And V is directly proportional to numerical aperture. So just recall V is A0A root over of n1 square minus n2 square. So this is for step index waveguide. If it is a parabolic index, then n1 will be replaced by nx. So this is nothing but the numerical aperture. That means if V2 is greater than V1, so the acceptance of the second waveguide should be greater than the first waveguide. So this is correct. Option C is the fundamental mode of the second waveguide is more confined inside its core as compared to the first waveguide, which is also correct. We have seen in option 1. So if V parameter is high, then the beta value will be higher. Okay, this is also correct. Last option is the cutoff wavelength of the fundamental mode is higher in first waveguide as compared to the second waveguide. Cutoff wavelength of fundamental mode. But if we recall the graph, the fundamental mode, that is the TE0 mode, it starts from 0 and diverges at value pi by 2. So it doesn't have any cutoff. So no matter guide it is, fundamental mode will be always there unless and until V is 0. V is 0 itself means this is not a waveguiding study. So that means whenever V is non-zero, the fundamental mode, it won't have any cut in the waveguide or in the fiber also. Only the higher order mode, they have the cutoff. Like if you see the TE1 mode, it starts from pi by 2. So that means if V is less than pi by 2, So it is this one is T1 mode, right? Starts from it lies between pi by 2 to pi. So if it v is less than pi by 2, then it won't exist. So I think this is clear. So this means the option C, it is option D, it is not correct. So the right answer is B and C. Okay. Okay. So it was all conceptual one. Now let us solve one numerical problem. The question 15, it says consider a planar waveguide with a refractive index profile given by n square x is n1 square for mod x less than d1. It is n2 square when d1 mod x d2, and it is n3 square mod x greater than d2. Other condition is given, n1 is greater than n3 greater than n2. So write down the range of propagation constant for the guided mode. So it is easy. I have already discussed it. So just look at the profile of the refractive index. So the profile is somewhat like this. So you have two depressed clad layer. We'll see what are the advantages of using this type of profile. Just to give you a hint, it's like these are used for dispersion compensation. We will see later in the course. This is NX, this is N1, this is N3, and this one is N2. So for the mode guidance in this co-region, we want beta to lie between N1 to N3. Other than that, it will be a radiating mode into the cladding. Okay, so this we have already discussed. So I think I can just write out the answer. So beta tilde, it should lie between N1 to N3. And second option, if N1 equal to N3, can such a waveguide support guided mode? So it won't support, right? Because if N1 is equal to N3, that means the profile is like this. This like this, so there will be no guidance. It's like uh, the wave is guiding along all this flat region. Okay, so there is no guidance. So no, it's not possible. Let us see. So the next problem, it's same. The consider symmetric planar. So we'll discuss mostly symmetric planar waveguide. Uh, and it is given N1 is 2.3, N2 is 2.2, D is 2 micrometer. Operating at wavelength 1 micrometer. How many guided modes will the waveguide support? So this is easy. So you just need to calculate what is the V parameter. So V is nothing but 2 pi over lambda 0 d by 2 root over of n1 square minus n2 square. So these are already given. So this will get I think 0.671 into 2 pi. And to find out the number of modes, we have to divide it by pi by 2. This will give 4 times 0.671, which is 2.683. So this number, it is less than the integer 3. So that means we will have total number of 3 TE modes. 2 will be symmetric, 1 will be antisymmetric. So the first part is 3. Next part, what are the minimum and maximum values of beta for the TE1 mode? So minimum and maximum value, this means what are the cutoff values, right? So if you recall, for guidance, for guidance of TE1 mode, the beta tilde should lie between N1 to N2, right? And beta tilde is nothing but beta by K0. So that means it should lie between K0 N2 to K0 N1. So maximum value will be K0 N1 and the minimum value will be K0 N2. N1 and N2 already given. So it will be 2.3 K0 maximum value and the minimum value will be 2.2 K0. This is easy. This problem is based on a symmetric planar waveguide. Uh, the question says, draw the first 3 T mode profile of the following asymmetric planar waveguide. So picture is not given, so let me draw it. There is a asymmetric planar waveguide. So this is and next this X variation N1, N2, and sorry N3 and N2. This profile is given. So what will be the first 3T mode profile in this asymmetric situation? So it will be symmetric to what we have in the symmetric planar waveguide, but the decaying length, it will be different in cladding 1 and cladding 2. Okay, so what I mean to say is so if you recall, for the symmetric one, for the symmetric one, we have this is x equal to minus a, x equal to a. Here it is n3, n1, n2. And from the profile, it is greater than n2. And if you recall, alpha, it is minus, sorry, alpha is root over of beta square minus k0 square, refractive index of the clad layer. So that means the penetration will decrease when we have higher value of alpha, right? Higher value of alpha means lower value of cladding refractive index. So that means because N3 is greater than N2, the penetration into the cladding for this clad, it is lower than this clad. Okay. So for the symmetric one, we have more penetration in this region this will be even and less penetration in this area. This region, it is larger than this region. And for the other higher order mode, it is the concept is same, just the profile will be same, but the penetration, the constant value will be different to the symmetric one, but overall the profile will look the same, and the penetration here it will be higher, and here it will be lower. Similarly, for the third mode, it will be higher in this region, then it will be lower. Okay. So is this clear to you? Okay, let me move to our next problem. So this will be the last problem for this live session. I do have two other problems, but I think it will take some time. So consider a symmetric planar waveguide with the refractive index N1 is 1.48, N2 1.46, and D it is 5 micrometer. And effective indices of supported T0 and T1 mode is given. So N effective T0 is given, it is 1.4772, and N effective TE1 is given, it is 1.4730. At wavelength lambda 0, 1.06 micrometer. Then calculate the angles that the constituent plane wave will make with the direction of propagation. So we need to find out the angle with respect to the direction of propagation for this case. Okay. So let us go through the concept first, how the angle is related to this refractive index. Sorry, effective index. So if you recall, E by x for T0, it is A cos x e to power I omega t minus beta x, right? And cos kx, you write it as e to power I kappa x plus e to power minus I kappa x over 2 e to power I omega t minus beta z. So this will give a by 2 e to power I. So just multiply the term with this. So we will get I omega t plus kappa x minus beta z plus e to power I omega t minus beta z minus kappa. So what is this form? This indicates a plane wave, right? The plane wave propagating along plus 6, sorry, minus 6 and plus z direction. In the second one, it's also a plane wave, but it is propagating along plus 6 and plus z direction. So graphically, you can draw like this. For the first one, if it is z, it is x. Then the first plane wave propagate like this, the second one propagate like this. So that means the modes, they are superposition of two counter propagating two plane waves which are propagating along plus xz and minus xz direction. Okay, so if we combine this, we have this plus x and minus x. Let's say this is theta and the angle that the ray makes. And let us say the propagation constant along the propagation direction, it is beta m, and along the x direction, it is, let us say it is alpha m, or let us say it is gamma m. Okay, so that means what is beta m? Beta m now is it is so so if you square it, so beta m square plus gamma m square. So this will give k0 n1 square, right? So this vector here, it is k0 n1 because this will be the maximum uh, propagation constant inside the medium k0 n1. So that means we have beta m as k0 n1 cos theta m, and gamma m, it is k0 n1 sin theta. And for effective index and effective for a mode m, it is nothing but beta m by k0, which is n1 cos theta. So this is the relation between n effective and the angle of propagation. N effective is already given. So it is given n effective for the zeroth order mode is 1.4772. So that means n1 cos theta m, it would be 1.4772. So n1 is given, it is 1.48 cos theta. So from here you will get theta m as 3.5 degree. Similarly for the next mode, which is 1.4730, so cos theta m will be 1.4730 over 1.48. So theta m, you will get 5.6 degree. So 3.5 and 5.6 degree. So we got option A. Okay. So this is how you can relate the effective index of a mode with the angle of propagation. So this will be the last question. So I have two more questions, but let us not solve now. We'll solve in the next live section. So till now, do you have any doubt? Let me clarify your doubts for the next 5 minutes, then we'll end the live section. So if you have any doubts on assignment or the tutorial or any conceptual, so please ask me now. If you have, you can ask me now. Then otherwise, we'll end the live section. So we have for this lab section, we mostly covered the symmetric, antisymmetric, planar waveguide also, and Okay, if not, then okay. So let me end the lab section for today. Thank you for joining the section. I hope whatever I have covered today, it is helpful for you to solve the assignment as well as for numerical understanding, conceptual understanding. Okay. So we'll meet on next Monday, same time, from 6 to 8. So please try to join the live section. Okay. So because if you join the section, you can easily ask me the doubts if you have any regarding the assignment or tutorial. So thank you for joining. We'll meet on next Monday. Okay. Bye everyone.